Okay, so just what I'll go through today is just a bit of an introduction on myself. I know Joe's already kindly done that. We'll look at some heat sources for heat pumps. Look at different examples, including how geothermal can be applied to hotels, as an example, leisure facilities, manufacturing, and I'll talk about a case study we've done in a water. System solution options we'll touch on. I'm going to look at the benefits then of the particular system we do that offers HTR. I'll delve a wee bit into that, free cooling, and also energy manager when you have it linked to wind or PV, your system. I'm going to talk then about Randalstown, the centralized heat pump system we completed that 4 years ago. And then we look at a decentralized system we've just completed recently with the Housing Executive in Northern Ireland. And we'll go through that. I'll then talk a wee bit about my own house that we completed in 2021. That was a self-built timber frame, 3,500 square foot house, and how we achieved £1 a day running cost. Look at a capital cost example between air source and ground source for a commercial project. Touch on the geothermal versus air source debate in Ireland and the differences between the two, and then finish off with any questions. So just a wee bit on my own background. I did my degree in environmental engineering. Started off working in an M&E consultancy and for an M&E contractor. Got great experience on them two roles, especially on commercial projects. Had a passion for renewables and heat pumps and geothermal. So in 2007, started working with a company, Schofields in Belfast, and they had started doing heat pumps in the mid-2000s, mainly ground source, solar thermal, underfloor heating, that sort of combination. When I started there was a lot of issues I came across with the systems. They weren't all plain sailing. So a lot of issues with system design not being right, some bad installations done by previous guys that were there. Some issues with the house fabric as well, and we'll talk about that at the end and how that can impact on a geothermal system. But I learned a heck of a lot in 3 years, just basically delving into what these issues were, and how we could re-engineer solutions to make them better going forward, better systems for the homeowner. In 2010, I set up then my own business, Daly Renewables. We're probably now the largest heat pump installer in Northern Ireland. We've done a mix of domestic and commercial projects. It's probably more commercial back in the early days. But there's been a good mix there of domestic and commercial. We've probably done around 400 to 500 heat pump systems at this stage. And then in 2024, we merged with B4B Group. And that's given me more time to go back to enjoy what I do, which is an engineer, and sort of do challenging projects and challenge myself. So it's been a really good move from that point of view. So in terms of heat pumps, when it comes to heat sources, we often think of shallow or deep geothermal or air source heat pumps. But there's not to be forgotten, there's heat to be availed in other sources such as sewers, supermarket chillers. Data centers is an obvious one, wastewater treatment plants, underground rail systems, commercial laundry facilities with a lot of waste heat, hotels, and industrial process / manufacturing. I'm going to talk about a couple of examples for the last two. But we partner in terms of the manufacturing company we work with, it's EcoForest. So they would have examples of projects done all over the world with different heat sources being used. So it's not just solely ground and air source. So looking at a hotel solution, and this would probably be more for a new build, but it's just to show that when you have your heat pump there in the center, there is the potential to take heat from wastewater from showers, the wastewater from the kitchens in the hotel. Could be combined with a air collection unit on the roof, and then also boreholes. So with the heat pumps that we fit, there is obviously a multitude of heat sources available to be used. It's not just always ground source or air source heat pumps. And this is just to show a simple schematic of what the potential is with geothermal. And then on the other side, we have your outputs. We've got a typical hotel with a heating and cooling requirement. It also have a heavy hot water load, and obviously pool heating. So some of the projects we've done, even on domestic, we have swimming pools installed with heated by heat pumps, and the HTR and the heat pump will produce a lot of that energy to heat the pool free of charge when it's on doing heating. And simultaneously, we can do heating heating, hot water production, and also when we're doing cooling in the summer, we can achieve hot water as a byproduct. So it's just to show the capability and offering with geothermal that you don't necessarily get with other technologies. This is a case study we'd completed about 3 years ago now. NI Water approached us at their Castor Bay site. So what they had was a process control room, which was sitting always in around 30 degrees all year round. Just equipment that was giving off a lot of heat, and they had 3 extract fans, just dumping that heat outside. So we come up with a solution of a ground source heat pump, with a fan collection unit. Um, so traditionally, when you think of ground source, you think of boreholes or horizontal pipework. But in this case, we're actually using a fan collector unit, and that's just simply a fan blowing air across the heat source. We're taking about 5 degrees out of that room, and then that's helped to decommission a boiler in the plant room. That heat then is being used for their offices. So the boiler that was used before to heat the offices is now being heated with a ground source heat pump. And the COP or SPF on that was in around 5.4 when we went to visit it about a year after installation. They now have the 3 fans turned off. As I say, their equipment's sitting at a lower temperature and they're really happy with the solution. And just to touch on the HTR that I mentioned in the hotel slide. So HTR is high temperature recovery. So basically when you have your heat pump operating and you've got a refrigeration circuit that's going up to 60, 70, 80 degrees temperature, we don't necessarily need that higher temperature for production of underfloor heating water or heating a tank to 45 degrees for hot domestic hot water. So what the HTR will do is a second smaller plate heat exchanger inside the ground source heat pump. And once that gas in our system hits 56 degrees coming off the compressor, it opens up the secondary circuit and dumps that excess heat that's being generated into the hot water system or the swimming pool. So you can see in the graph on the right where you have your baseline temperature of 45, for example, and then the heat pump when it's on heating mode can be topping up the hot water to a higher temperature free of charge. In our experience, this really only works in buildings that have a higher heat load. So when the heat pump's having to work harder, it works really well. I have this in my own house, but because we have a low energy house, the HDR doesn't function as well because we're running our underfloor at really low temperatures, so it doesn't just kick in as much. Geothermal cooling is another benefit, and we'll talk again at the end about my own house and how we applied that. But with geothermal, you have free cooling and active cooling. Free cooling is basically taking the temperatures in that borehole or the ground collector, the horizontal loop, and putting that through an intermediate heat exchanger that then is being delivered directly into your fan coils or your underfloor heating system. So it's taking that temperature of 10, 12 degrees in the ground and basically transferring that into your heat emitter. And at the same time, that heat that's in your building will be put back into the ground. And then the benefit of that is that you're coming in at a higher temperature then in the winter months when you start to take heat out of the ground again. Active cooling is actually then running the compressor to chill that water down to a lower temperature. And then in our case, in our own house, we have that set to 18 degrees. So if it goes above 18 outside on the sensor, our system knows then to go into active cooling mode, and it works really well. And I'll talk about that at the very end. Um, Energy management. So the particular system we do, if there's PV on the roof, there's a wind turbine, we fit a little meter on the incoming power supply. That's just giving information to the heat pump as to what potentially is being exported back to the grid. So in our particular scenario with this setup, if we have more than 0.5 kilowatt in domestic going back to the grid over a period of 5 minutes, we can trigger our heat pump to come on and start using that electricity that's been generated for free on the roof. And you can see in the stat on the bottom left that that particular month of October, 54% of our production was generated with the excess mode or surplus mode, which cuts down obviously a lot on the cost of running the heat pump. The graph on the right then shows your solar kicking in, which is the green, and then the blue is more or less the heat pump mimicking what the solar is giving it. So we'll actually manage the revs per minute of the compressor to match exactly what the PV is giving it, and it works really well. I was out with a customer yesterday, and he was saying to me he's only had his PV run for a week or two, but he's noticed in a couple of days, the hot water's gone up to 60 degrees on the days that he's getting a bit of production from the solar. So moving on to the different options with heat pumps in terms of looking at sort of heat networks, we've got centralized or decentralized solutions. Centralized is where you have your main plant in the plant room, and then you've got heat distribution pipework feeding all the flats or apartments. And you can see in this example, we've got boreholes shown here and also a fan collection unit on the roof. So both of them can be combined as a heat source. And the EcoForest heat pump that we fit will have a control system that will modulate between the two. So when it gets to a certain temperature, if it thinks that it's better to use the fan collection units, it'll use that solely, or it can use both. The benefit of that system is that you don't have individual units inside the home or the flat, and it's lower maintenance because you have your plant just in a plant room. It's a good solution for high density housing. The decentralized option would work differently. So you'd have a shared ground collector loop, and then you could have a mini heat pump then in each apartment or flat. I suppose the advantage of that is the tenant owns their own particular unit, bit like owning their own boiler, and have a bit more control over it. And then they can pay their own bill, whereas the other option, you'd have to actually bill it out in terms of metering the tenants in whatever way you want to do that. I know with Randalstown, I think they just build it into their service charge. So they probably just, there's heat meters fitted, but they don't have to be too, strict in terms of reading them. They'll maybe check them once a year. Um, and then looking at that a bit closer, so the centralized system shows it here a wee bit better. You have two heat pumps in a plant room, buffer tanks and hot water cylinder. You can have a larger hot water cylinder in the plant room distributing water to all the flats or apartments, or you can also put a smaller hot water tank into each apartment. So just to gain the benefits, less maintenance and servicing costs. You've only one particular plant that you're maintaining, more habitable space in apartments for tenants. You can have a central PV array if you've only got a certain size of roof that can link to your ground source heat pump rather than having individual inverters and panels linked to all the apartments. Heat meters are required if the tenants want to be billed separately. And then obviously there's no harmful emissions. And that was one of the things with Randalstown. They were looking for a solution that was getting away from oil or gas. It was just a difficult site to get, gas connection to. But now that they have the heat pumps in, they're really happy with the fact that there's no, gas top-ups and oil is being delivered to site. There's nothing like that, and it works really clean. It's really clean. It's all very smooth. So the decentralized system, you can see from the photograph here, it's a small type. That's a mini ground source heat pump. And that would be a case where you're taking the heat from the shared ground collector. You'll have a loop, say, in a common service area, delivering energy up through the building. And then each mini heat pump will take energy off that loop, that ambient loop, and then connect into the ground source heat pump. The benefit of this, I suppose, it's a direct replacement for a boiler. If you have a retrofit project, the heat pump, this particular model can achieve 70 degrees flow temperature. It's got a very small footprint, smaller than a normal domestic appliance. Particular heat pump can produce hot water, heating and cooling all in one unit. You can be flexible in terms of your hot water tank. You can size that appropriately for the building. No buffer tank required as the heat pump is modulating its output. And then with our particular solution, all the equipment in terms of the pumps, the three-way valve, the switch between heating and hot water is all built into the one unit. So you don't have any external pumps or nothing like that, which is one of the benefits of it. So looking at the Randalstown project, we were approached by Rural Housing Association about 5-6 years ago. They actually went to look at a couple of schemes that we'd done previously just to get a bit of confidence in the system and speak to people that have had it in for 7, 8, 9, 10 years. They liked what we put forward. We proposed the communal system where there's two 22 kilowatt ground source heat pumps, EcoForest, in the plant room, and they're linked to 640-meter boreholes in the car park. So you're actually one of the first trades in on that project to do the boreholes before any of the civil works was done in the building. Each apartment then has underfloor heating. They have a mechanical heat recovery ventilation system and a 250-litre hot water tank. The system SPF is averaging around 4, with domestic hot water heating it up to 58 degrees, probably a wee bit higher, but then we have to allow for that just slight drop off in terms of circulation of that heated water up through the building. There would be a 3 to 4 degree loss in that. Hot water is heated a lot by the HTR function in the heat pump that I mentioned earlier. And we had a good bit of input in the design, so there was an M&E consultant on it. We worked closely with them. They actually had HIU heat interface units on the scheme, and we proposed to replace them with just two simple heat meters, because we were worried about losing sort of 4 to 5 degrees delta across that plate heat exchanger with the heat interface units. Plus, it didn't really need it. I didn't see any other justification for having them. We also put forward very simple controls for the homeowner. They have a one master stat in their hallway, which is simply up or down, and then they hit a tick, and that's how they set their heating. So there's only one stat in each apartment. The running cost to date is averaging around £15 a week for the winter months, and that's all their heating and hot water, which they're very happy with. So some of the learnings from Randalstown, again, simple heating controls works best. Just one of the philosophies I would have is don't give people controls that they don't know how to use. We even found over the years that a simple enough time clock for a lot of people can be very difficult to program. So we try and stay away from all that kind of stuff and keep it very simple. Avoid using unnecessary equipment. Mentioned the HIU units. In that scheme, they fitted 3-port valves, which we didn't think were required, but again, it was on the design. So that was simply to divert the heated water from the underfloor manifold back to the plant room. But a 2-port valve would have been sufficient there, because I actually had some issues at the start with the 3 ports not diverting the heat correctly. Better to work with the same designers and contractors. And mentioned the example of the borehole. So we would have spent a lot of time sort of hand holding the contractor to start to say, like, here's what he's due, and here's how you prepare the site for the borehole rig coming in. There was a lot of time spent on our side, sort of educating them because they hadn't done a geothermal system before. But hopefully, if they ever do one again, they're a bit more knowledgeable. Um, Educate the tenants. So that's also really important that you're handing over a system that they know how to use, or they're comfortable with sort of how the controls work. And again, in their case, it's very simple. They don't really have to do anything to set their temperature, and the hot water is there on demand, so they don't have to program hot water at all. Be in full control of the heat emission and ventilation system. I've just found from experience where we've done the complete installation of the underfloor and ventilation, you don't have one party doing the heat source and a different party doing the heat emitter. Whereas we had full control, and there's been zero issues in terms of getting it all linked up and working efficiently. And then the final point is just M&E consultants would kind of need our input at design stage. So it's probably best to work with them at a very early stage, so that we can sort of base the design on previous experience, and when we know what works best in a lot of cases. That was the schematic, just showing the 2 heat pumps for Randalstown. We've got the E-manager set up. There's no PV on the roof yet, but it's all pre-wired for the energy management system. Two heat pumps linked to 2 separate buffer tanks. We have a buffer tank for LPHW and a buffer tank for domestic hot water. And then 2 pump sets pumping that heated water up to all the 9 apartments. And you can see then in the apartment you have an underfloor heating manifold and hot water cylinder in each apartment. And then each of them lines will have the heat meters fitted to them. And then looking at this Strabane decentralized system, so it's a trial project just done by the housing executive recently, where they asked for 3 air source heat pumps to heat the 3 bottom flats, and then there's 3 ground source heat pumps heating the upper flats. Each flat is in around 60 square meters. We did chat to them at the start about maybe going with one system to do everything, a bit like Randalstown, but they were keen to just do this as a trial so we could understand where they were coming from. The heat pump is the heat source for the ground source is 2 90-meter boreholes with 32 mm pipe in each borehole. We actually reduced the borehole depth, which the consultant had on his spec. He had at 300 meters, but when we done our own heating calculations, we lowered that down to 180 meters, and so far so good. Like the temperature coming in when I was there on site recently was in around 6.5, 7 degrees. So we're getting good temperatures from the borehole. The 3 ground source heat pumps share the boreholes, so it's a mini heat network, I suppose. And it's all worked really well. And I'll just come on to that in a second, the difference even in the ground and air source heat pumps. And then we were involved in doing some M&E schematics, and they were approved by the consultant, but I also gave them to our contractors who fit the pipework. So it's important that they have that information like these contractors we work with typically have been working with us a long time, so they don't necessarily need it, but it's always good to just make sure we have that covered off. You can see in the photograph the borehole rig on site, and then they have PV on the roof as well, of the flats. These flats, by the way, sat dormant for I think 15, 20 years. So they've been brought back to life, and it's great to actually see it in the area, you know, a building like this being brought back to life. McCuskers were the contractor on it, who were a really good company to work with. And DH Mechanical were involved in mechanical, again, great company to work with. So all went really smoothly. They did external wall insulation as part of the deep retrofit. So that seems to work really well in terms of the performance of the heat pump system. That's a schematic there of what we've done in terms of the fitting of the heat pump. And we have the EcoGeo Lite, the 1 to 6 kilowatt on the ground source. One of the things we recommended was the no TRVs fitted on the rods. We didn't want that. We didn't want TRVs short circuiting the heat load going through the radiators. So it's better to balance your system and have your radiators, balanced correctly rather than relying on TRVs. And it just means that there's more volume in the system when the heat pump does come on. It's not heating one radiator, it's heating all the radiators in the flat. And then the picture on the right shows the mini heat pump, the EcoForest EcoGeolite 1 to 6 kilowatt ground source heat pump. That's a small inline buffer tank just to increase the volume of the system a wee bit as well, which probably more thing for the air source heat pumps when you're required to do a defrost, but we put them in for the ground source as well. So just looking at performance so far for Lisnafin, the running cost for the ground source heat pump. So interestingly, the lowest there is 50p a day over the winter. And you can see on the bottom left photograph, that was a photograph taken on the 9th of February, and that's how I worked that out. It was 16.6 kilowatts used in electricity. There was 62 kilowatts of heat produced in total, but you can see from the figure above, half that there went to the hot water production. And then the next photograph over, exact same system, but the electrical usage is 49 kilowatts. So when we looked into this, I actually could see this on the controller of the heat pump. One tenant had their flat set to 20 degrees, and the other one had their flat set to 24 degrees. But you can see there's no difference in the SPF of the heat pump, which is averaging around 5.5 there in February. And then it's not a great photograph, but just to show on the right, the air source heat pump down below on flat A, 64 kilowatts using electric, and the SPF on that was coming in around 3.8. So fairly significant difference in the two systems. Although, I suppose, important to caveat, the ground source heat pumps are on the upper floor, which they will get obviously a wee bit of heat coming from below from the heat pumps fitted on the lower floor, which is the 3 air source heat pumps. So just to touch on my own self build, so we have achieved a run cost of £360 for the year, and I'll show the split of that in a second in the next slide. But how we went about achieving this, I say it's a timber frame house and it's a completely sealed box, so completely airtight, airtight tape done on the inside and outside of the building. All thermal bridges were identified and dealt with, and all insulation done without any gaps at all. We have large expanses of south-facing glass, so in the winter, well, we haven't had much solar gain in the last 6 weeks here, but most winters we're getting a lot of heat gain from the glass, which obviously cuts down the heat load. The flip side of that is that we need to cool the house in the summer. So our geothermal heat pump, very minimal cost because we're only running a couple of circulating pumps, will provide free cooling. And as it gets hotter outside, we can kick into active cooling. So last April through to September, October, our heat pump ran actually on cooling mode for a good chunk of the year. And that keeps our house in around 23, 24 degrees, which is perfect. Our heat pump is fully integrated with our solar. As mentioned earlier, we have the energy meter. So if we do get days of solar production, our heating is boosted and also our hot water is boosted. We go to higher set points in both. We have a 100 mil sand cement screed on the ground floor. So the idea of that is that you have a thermal lag. So when your heat pump is injecting a bit of heat at a low level throughout the day with the solar feeding it, you then want the advantage of that there is that your heat is coming up perfectly in the evening time when you want it the most. Whereas if you had a liquid screed, it's quite more responsive. So that heat you could feel then potentially a lot earlier in the day, which is what we didn't want. We have an economy 7 tariff, because we've got electric cars, so that's used to charge our cars off the lower peak or lower tariff at night. We also use that to top up our battery, our 10 kilowatt battery at night. If it's a winter day and there's not much solar predicted for the next day, we'll take 10 kilowatts off the grid at the cheaper rate. Underfloor heating is used primarily on the ground floor. It's only used sort of 5% of the year for heating upstairs, but it's used the majority of the time for cooling in the summer. With the cooling, we find that works best when you have hard surfaces. So all our flooring is tiles or laminate flooring, which works really well. Carpets would just inhibit that sort of cooling effect slightly. So that's the reason we went with that type of flooring. Short hot water runs. So all our wet rooms in terms of en suites and main bathroom are within about 3 to 4 meters of our main hot water cylinder. So very short hot water runs. And all our heating pipework and mechanical ventilation ducting is all within the thermal envelope. So in a lot of the domestic projects we do, because there's no thought put into mechanical ventilation in the early stages, a lot of the mechanical ventilation units go up in a cold attic space. Now it's all insulated, the ducting, but there still will be a certain amount of loss when you have an attic that's sitting at -1 outside on a really cold day. So all of ours is within the air tightness layer and the insulation layer, and then it just really improves the performance of the overall heating system. And then just some of the stats then coming out of that. So our SPF on our heat pump, if you look at the performance on the data sheet, it's rated 4.5 our heat pump, but our actual real life performance is 5.7. And a lot of that obviously is down to the fact that it's cooling as well. So we're putting that energy from the house back into the ground for 4 or 5 months of the year. Because of that SPF, that actually means that 83% of our energy comes from the garden. So the heat pump compressor is only providing 17% of the energy to produce our heating or hot water cooling. In our first year when I monitored the system, 45% of our overall electrical requirement was covered by our PV array, which is 3.6 kilowatt inverter on the garage and 5.3 kilowatts of panels on the roof. Our heat pump operation, when you broke it down, is 23% hot water. This is for last year, 32% cooling operation, and 45% heating operation. Average mean temperature is 21 degrees in the winter in our house and 23 degrees in the summer. And then the run time for the heat pump is in around 4 to 5 hours per day on a cold day. So what that means is that your geothermal collector in the garden, which is in our case, it's 600 meters of pipe, 40 mil pipe, gets 20 hours of recovery per day, which it means it's getting loads of time to re-energize itself. And going back to the early days of 2007 when I started doing heat pumps, it was actually the flip side of that. So we had heat pumps installed in houses that were really badly insulated, and the heat pump was running 20 hours a day and only getting 4 hours recovery time. And that really has an impact on the performance of the heat pump long term. Carbon savings massive, 90% versus an oil boiler if you compare the two. And then as I say, the run cost is in around £360 for the year. And then £245 of that is for the heating and hot water. So ground source versus air source in Ireland, some of the key differences for us is the higher COP. We've already seen that a wee bit with the Lisnafin case study. Because you're getting that stable temperature of 8 to 12 degrees all year round, it's just a really good base load to be starting from. More consistent output. So obviously in the winter months, the air source heat pump has to do a defrost cycle. And when it's doing that, that could be 5 to 10 minutes of, taking energy back from the house and getting the heat pump defrosted and getting that built back up again, that temperature. So obviously you don't have that loss with the ground source heat pump. Quieter operation and no visual impact outdoors. So obviously the heat pump, the ground source will sit inside your property, and we try and steer away from putting them in a garage. We like to have them somewhere central in the house, ideally. So we're shortening the heat and distribution runs to the underfloor heating and hot water cylinder. Longer life expectancy. So obviously the air source sitting outside, and it's got more components in it. It's got a 4-way valve to do the defrost. It won't last as long as a ground source heat pump. When I went to Switzerland in 2007, we started working with a heat pump manufacturer over there. The engineer that I visited took me to his own house. His heat pump had been in 28 years, his ground source heat pump, and he hadn't had to do a thing with it. And that just proved to me that this technology is proven in different countries, and we just need to get going with it here. Um, in Ireland, actually, we don't have the best climate in terms of humidity, and so we've got a quite damp climate, which means our air source heat pumps have to actually do more defrost cycles than some other European countries. And a lot of our heat pumps go in because it's a small island. We were often near coast locations, so again, not ideal in terms of longevity if the heat pump's sitting outside. And then reliability. So having done, sort of that amount of heat pumps over the last 20 years, we've just found if there's ever a cold snap, ground source heat pump is just never affected. If you ever get an issue, it's always usually an air source heat pump, and that's just being honest and saying what we've experienced over the years. The free cooling is a major plus with the ground source. If you obviously you can do cooling with your air source, but it's active cooling, it has to run the compressor, and there's a cost to doing that. And then less likelihood of getting stolen. So we've heard of a case recently in London where there was 27 air source heat pumps that were stolen from a site on a Saturday. And because obviously these things are expensive and people are starting to get an awareness of what they do and how valuable they are. Um, and then we did just a quick presentation recently to an architect. It was a site of 32 houses, and we put forward a communal geothermal system. So just to show, rough costs if you had an air source heat pump, because it was near the coast, it needed Blygold treatment as well. And factor in the cylinder, it was in around 235 grand for the complete system. Whereas if they were happy, it was a community that's going to look at potentially older people. So I put forward the notion of the communal system. So three, not large, but 22 kilowatt ground source heat pumps. Bearing in mind the buildings were in around heat load of in around 2-3 kilowatt potentially. So, you put in a heat pump, an air source heat pump to do that heat load. It's quite small heat load. It nearly doesn't justify putting a heat pump, but that's what the architect had sort of preferred that option. But look, we put this forward to them. We just said that with our experience in Randalstown, and it worked really well. You'd actually be saving about 40 to 50 grand on the installation cost if we're open to doing it. That's it, everybody.